let's take a look. So today we're going to talk about the last unit we have to talk about, which is antiderivatives, a scary word I mentioned last class. And we're going to talk about them in two senses, which the title slide gives away, graphically and numerically. Graphically, I just mean what does an antiderivative look like? How do we graph the antiderivative given the derivative? And numerically, how do we actually compute these things? How does the math actually look? All right. So first off, the key fact about an antiderivative is that it's a family of antiderivatives, right? There's not just one for any function f, and I'll give you an example. So the defining factor is that the derivative of your antiderivative is your original function, right? So big F prime is little f, in other words. So in order to show you that these things are a family of functions, in other words, they're non-unique, I'm going to give you three examples of antiderivatives of this function. Okay, so I know that the antiderivative of x squared is x cubed over 3, and the antiderivative of 2 is 2x. Okay, but if I put a plus pi on the outside here, then when I take the derivative, I still get back x squared plus 2. Okay, and if I do this again with like a plus 10, I get the exact same thing. And we all know that that's because when I take the derivative, that the derivative of a constant is just 0. Okay. And remember, last class, we talked about the fundamental theorem of calculus. So if I had, 3 to 4 of this x squared plus 2 dx, the fundamental theorem of calculus tells me that as long as I have one such big F whose derivative is the integrand, then I can apply the fundamental theorem of calculus. So let's do that with the first function. So we get x cubed over 3 plus 2x plus pi. And then that's evaluated from 3 to 4. Okay. But what we should notice here is that when I plug in, I would get 4 cubed over 3 plus 2 times 4 plus pi, right? Because I don't have to plug in anything there. And then I subtract off the other term, so I get 3 cubed over 3 minus 2 times 3 minus pi. So any constant that I had on the outside for this big F is always going to be added over here and subtracted over here. So in other words, they're always just going to cancel each other out. So my big F doesn't care what this constant is on the outside. So this constant doesn't matter, whatever I'm adding on the end. So that's why I'm saying these antiderivatives are not unique. There's a whole family of them for any little f. Okay? Okay, so I'll give you some examples in the slides. So in general, the antiderivative of some function little f is any function of this form for our example. Okay? And this is because it didn't matter what plus c we added, as long as this piece still gives us, when we differentiate, what we wanted all along. Okay? I'm going to look for questions in the chat. Does that make sense so far? Is everyone okay with that? All right, Michaela's good. Aaron's good. Zoe. And Yuling and Brett. And Alex. Awesome. Thanks, guys. All right, we'll keep moving. Like I said, it's going to be a pretty short class today. So now we want to talk about sketching antiderivatives. So I want to do an example for you. So you can look up this function, but some of you might recognize it from statistics. This is a bell curve, but it's not a normalized one. So it's not like a normal distribution, which is going to have area 1. It's just any regular bell curve. So this is the function e to the minus x squared, right? And this is the y-axis, and then below is the x-axis, like that. And the question is asking us to sketch the antiderivative. But we already know so much about calculus at this course, so we really don't, there's really nothing new here to learn. So first of all, we learned that antiderivatives are not unique. So sketching the antiderivative is maybe a bad way to put it. It's maybe sketch a antiderivative of this function, right? So we just saw that shifting our function by plus c doesn't matter. So I'm going to actually sketch two of these just to show you how they would differ on a graph, okay? So let's pick our antiderivative to have to contain this point. And I haven't told you this yet, but it's true that if I fix one point of our antiderivative, then that plus c is determined, which means that I can graph this with confidence, okay? So I fix my point at the origin that my curve has to contain, and now I notice that e to the minus x squared, this is always positive, okay? And it's growing slower to the left, and then it grows faster as we get toward the origin, right? That's over here. And then it starts to slow down again. So it sort of looks something like this. It almost looks like an arctangent, but it's not arctangent. Okay, so that's one graph of an antiderivative. Okay, and here this is the antiderivative that I fixed. Big F of 0 had to be 0. Okay, and what I said is that any antiderivative is just the plus c shift of another antiderivative. So that means that if I were to draw another one, I could draw it up here, and it's going to be a mirror image of the thing below it. It's the exact same thing, just shifted up. Okay? And I could even draw a third one, right? They're all the same. The only difference is that there's a vertical shift. So there I've just drawn for you 3 antiderivatives of this function. Okay? And notice that if you're forgetting sort of how to draw the original graph of something, just remember we want to look at the sign of the derivative, and then we want to look at how the derivative is changing. So here it was positive and small, and then it was positive and large, and then it was positive and small again. And that is how I informed the shape of my graph. I see maybe I have a question in the chat. Oh no, U-link's good. Okay, just sent late. Okay. All right, so now we're going to use this knowledge to define a new, slightly new object. So again, we have a similar setup. We have a big F, and we're saying that the derivative of big F is little f. Okay. And we're going to define the indefinite integral of little f to be, we're going to denote it like this. So notice the main difference is that the indefinite piece, right? So the definite integral had bounds here, like 0, 1, for example, but here we're not requiring any of that. So it's going to be f of x, big F of x, plus c. Okay? And c here, again, is just any constant or real number. So we're adding that c to show that we know that it's not actually equal to just f of x, because the all these antiderivatives are differing by shift, so we have to include the c to show that we know that it's a family of things. Otherwise, this definition wouldn't make sense. Okay. Okay, so c is some constant real number. Great. And now we've defined a slightly more general thing than our definite integral. Okay, but the properties are all going to be the same, and that's going to be really nice. So first off, if f prime is 0, then the integral of f prime, so f prime being 0, that means nothing's changing, right? Our function is just staying flat, it has no increase, okay? Which means that we should get some constant over here. Okay, so it's just like saying the integral of 0 is 0 plus c. Okay, so that's exactly what we expected, and that's what we got, which is good. And now let's take a look at a second property before I check in with people to see if we're okay. So if f big F and big G are both antiderivatives, so there are two different antiderivatives, potentially different, they could be the same, then f of x is g of x plus c, where c is some constant real number. So we already kind of saw that, and I already said that. That was when we looked at these graphs here, we noticed they were all just vertical shifts of each other. And that's precisely what this theorem is saying. It's saying that any two antiderivatives are just differing by some c, okay? And these c's that we're writing here, like when you write plus c or whatever, it's just a placeholder, right? It's not like a determined thing. It's just, we know there is a c such that this happens, okay? Is everyone okay with that? Do we have questions? All right, so it's all good. Aaron's all good. Michaela, Yuling, Brett, Alex. Awesome, thanks guys. All right. So just as we had with the definite integral, if we have a constant, and I'll say this in a moment with the linearity slide, but we can pull it out. And the integral of 1 dx, right? This is just x, so it's kx plus c. And we always have to remember to add the plus c now that there's nothing here and here. These are empty, so we have to be precise and add c. Okay, so that's nice. That means the integral of a constant is a line, which is what we would expect, because that's a constant rate of change, right? And the only guy that we know that has a constant rate of change is a line. The other thing is, when n is not -1, the rule we've been using so much of and sort of guessing and checking is actually formally true. So when n is not -1, then I get 1 power higher for my x, and I have to divide by that power that I'm raising it to. And then, of course, I have to add my c because it's indefinite. So why can I do this for -1? Well, the power rule doesn't work the same here, because if I tried to do that, I would get x to the 0 over 0, right? And that doesn't make any sense. So I think I'll show it in a moment, but the integral of x to the -1 dx is somewhat surprisingly the natural log of x plus c. So this is going to depend on where you're looking, but I think we might have to include absolute value here. Right. Okay, so this is just what I was saying. Yeah, and that was my errors. You have to include the absolute value here, otherwise it doesn't make sense for negative numbers, because of course natural log doesn't take in negative arguments. Okay, this next one is not going to surprise you at all. We talked about how the derivative of e to the x is e to the x. So of course, when we integrate e to the x, we should get e to the x and then plus c again. So very standard, just some basic identities to keep in mind that might help you. Here, we've already sort of covered this again, but it's still useful to know. We saw that sine and cosine have these sort of periodic derivatives where if we differentiate one enough, we get the other, right? And vice versa. So what we expect to be true here is that it's sine of x plus c. And what this theorem tells me is that indeed it is all the time. There's nothing weird going on there, exactly what you would expect. And similarly, oops, didn't mean to cross that out. Similarly, integral of sine of x is going to be minus cosine of x plus c. Okay, just like you would expect. Okay, so nothing crazy here. The other thing I wanted to mention is that the nice property of linearity holds for indefinite integrals too. So just as I had with definite integrals, I can also split up these integrals into each piece. So if I have two functions added or subtracted inside the integrand, I can split that up, and I now have two hopefully easier integrals to deal with. Or if I have two integrals, I can combine them and maybe have some cancellations and make my life a little bit easier. Okay. And then the last thing with linearity is that we can pull out constants. So in other words, if I have a constant inside the integral, which I briefly mentioned this earlier, I can just take that out, and then all I have to do is deal with this thing. So that might make my life a little bit easier. So now that these are all phrased in theorems, you can take these properties for granted and just ingrain them in your head and in your practice. And that should be fine. So let's do an example. I just threw a lot of properties at you. Let's do an example to see how they're used and to make sure we're using them correctly. So first, we have this horrible thing in here. Well, maybe I'm going to make my life a little bit easier and apply linearity of the integral. So if I do that, I'm going to split up all these things into their own pieces that are hopefully easier to deal with. And I'm actually going to use linearity here to pull out the minus e, giving me integral of just dx. But of course, I could have actually left that minus e in there. And then we have a theorem that tells us that if I had a constant k in there, then it should be kx plus c. So it should be minus ex plus c. Okay. So I'm going to put that in parentheses, and then we have plus, and then this integral here, that's the anti-power rule, right? We just saw that. So I have to raise it one power above and divide by the power I raised it to. So 77 plus 1, 78, divided by 78. And then also plus c. And then over here, I can pull out this pi. And so I'm just looking at the integral of sine of x dx, which I know by the theorem is just minus cosine of x plus c. And then I had times pi, so I'm going to add that in, pi c. But now I can do something that might surprise some of you who haven't seen this stuff before. But what I said is that c is just some parameter, and it's just some constant. So I don't actually care what it is. So I'm just going to gather up all my c's and make that a different c. So in other words, I'm going to say that this is equal to minus pi cosine x plus x to the 78 over 78 minus ex, and then I gather up all my c's, including the pi that's attached to the c, and I just say plus c prime. Okay, and I don't really care what it is. If you give me a point, though, I don't want to deal with 3 different c's and have to sort of juggle this. I just want to deal with one parameter that I'm worried about. So that's how I do that. Any questions about that, or is that okay? That's it. So I'll stop the recording as I look for questions.